Hello class, this tutorial is going to cover chapter 10.1 homework, and we're going to be looking at correlation, which is essentially looking at the relationship between two variables. So in this question, to start with, this is question number 4. And what's the test to claim if there is a linear correlation between weights of bears and their chest sizes? So it's not talking about if there's a positive or negative correlation, it's just asking if potentially does the chest size of a bear go up, does the weight of the bear go up, or vice versa, or in the kind of different directions which you may not expect. So would a bear with a larger chest size be of lesser weight? These are things that we can find out through correlation. So essentially, correlation is the statistic for correlation is little r, or rho. It also looks like this. So this is a rho. This is a Greek letter rho. And the correlation coefficient can either be positive up to 1 or negative down to -1, or it can be 0. So that's the scale that it operates on. We have a critical R, just like we have critical T or critical F, to be able to determine if the relationship is statistically significant or not, if we go past that critical R in the direction that we're intending. So first, if we kind of establish our hypothesis of our null hypothesis would be that rho would be equal to 0, meaning there would be no relationship. And our alternative hypothesis would be if rho does not equal to 0, which would mean that there is some positive relationship, or some relationship exists, whether positive or negative. Okay, so let's first, that just gives us the output here of this question. Identify the correlation coefficient R, or rho. Here it is, correlation coefficient R. I'm going to round to 3 decimal places, 0.953. Check answer, fantastic. Identify the critical values. So there are 2 critical values at R, or there's 1 critical value at R. Since this is a two-tailed test, that means there would be 2 critical values. If there was 1 critical value, we would expect that to be true if it were a one-tailed test, meaning we're expecting rho to be greater than or less than 0. Okay, there are 2 critical values. Here we can see plus minus, so it can be either greater than 0.26 or less than 0.26, negative 0.26, and that would be considered statistically significant given our alpha, our significance level of 0.05. Okay, so this value will change depending on the number of samples we have within our statistics. So if we're looking at an n of 5 or 50, it's going to vary. So the critical rho here, round to 3 decimal places, 2.268. Check answer, fantastic. Okay, and here you can be able to do the interpretation on your own. That's a huge thing that you should have practice with. Then I'm going to go to the next question, number 5. Yep, I'm okay with that. So here's an interesting one. So now we have to kind of match the graph that they gives us here as for options to the data that we have. And so we're going to go ahead and open this in StatCrunch. Bring it over. And here, before, I'm not going to be doing any stats. I'm just going to be starting with a graph. And this type of graph is called a scatter plot. But it is given different names. Yes, they call it scatter plot here too. So I'm going to make sure that x goes to x and y goes to y. I don't really need to worry about any of these other things here, as it's just plotting the data. I'm just going to compute, and I'm going to look for something that looks like this kind of curve that it has here, this one. Okay. Find the linear correlation coefficient R, then determine whether there is sufficient evidence to support the claim of a linear correlation between the 2 variables. Okay, so now I am going to go to stat. I am going to go to, not non-parametrics, regression. I can still do simple linear, I believe. So this is still going to give us rho. All right. here it is. So this is called simple linear regression, but simple linear regression and correlation between two variables is still going to give us the same results. Okay, and if I look here, here's my data. The red line is the fitted line of the correlation, but in a correlation, we're just determining if the relationship exists or not. We're not really looking at intercept or slope or anything like that at the moment. Okay, that's in future stuff. So the correlation coefficient, 0.81, round to 3 decimals, 0.818. All right, check my answer there. All right, and then I can still go to, so here I'm only going to be paying attention to the slope. Okay, so the slope is determination as if their slope is greater than or less than 0, or essentially, yeah, the estimate is that for every increase that I make in the x direction by 1, I'm going to see some y increase in the y direction here. So that's what this fitted line is showing us here. Okay, and that's essentially what regression does. But if I want to be able to determine the statistical significance of it, I can do that here as well. So I'm going to say there is sufficient evidence to support the claim of we're not nonlinear, even though this is a curve, they're still looking at linear regression, that there is sufficient evidence to support the claim of a linear correlation between the variables. Okay. Identify the feature of the data that would be missed if part B was completed without constructing the scatter plot. And so you already can kind of see that this data does not fit directly on this line, you know, as if it were something like this or something like this, right? So if you didn't look at the data and you plotted and you did the correlation, you would basically be able to say that this is a perfect fit to this line. This is not a perfect fit, so there's some variance here, and it looks like that variance is somewhat systematic. And the fact that near the extremes of our x value, we have some bias away from the line in the negative, whereas in the middle it goes into the positive. You don't need to worry about that, but essentially what it's asking for is that the scatter plot reveals a distinct pattern that is not a straight line pattern. Okay. Next question, same thing. This will be good practice for you to do. And then looking at what would be a good last question here. Let's see, we'll go up to 7. All right, this one's very interesting. Okay, do the data points appear to have a strong linear correlation? So here's our data points. Don't you need to really look at the question right away. Let's make it a little bigger. All right, so we see here if you are a kind of very straightforward or kind of realistic statistician, you would say that really there is no relationship between this data. This point seems to be an outlier, and that if we did any statistics on that, we wouldn't necessarily be able to trust it because this one individual seems to be an exception to the rule, and the fact that most of the data basically has no relationship. If I drew a line just through this data, it would just be a straight, it would just be a horizontal line. But since there's influence, heavy influence by this x, it may throw off our statistics, so we really always should look at the data and make sure that we understand exactly what we're plotting and trying to interpret from our statistics. And points have a strong linear correlation. Let's see, examine the pattern of all 10 points and subjectively determine. So I don't know what it's asking us here. I'm going to say no, because that's my answer. Your answer, the correct answer is yes, because the points lie in an approximately straight line. Do the data points appear to have a strong linear correlation? I mean, what is the value of the correlation coefficient for all 10 points? So this one's tricky because now essentially we have to enter in the data ourselves, which is kind of a bummer because I don't really want to do that, but we can do it very quickly. I'm going to delete the column here and delete the column here. So since I can see, I'm going to make it even bigger so I can look at it here. I have 3 points at, so I'm going to name this x and name this y. I'm going to put in all the x values first, so this is my x. So I'm going to go 1, 1, 1, 2, 2, 2, 3, 3, 3, 10. Okay, 1, 1, 1, 10. Okay, now for y, I am going to go with the data. I have to match it up. So for the one here, for these three ones, I'm going to do 10, 9, 8, 10, 9, 8. I'm going to do the same thing for these 2s. 10, 9, 8. Then the same thing for the 3s on the x. 10, 9, 8. And then I have, let's see, this looks like 2. 2. Okay? It's very important to make sure that this point is represented in your data correctly, just like every other point. This is point x at 1 with a y at 8. X at 1, y at 8. If I mix these things up, it's not going to look the right. So one thing you can do is come back over to your scatter plot. I'm going to put in x, I'm going to put in y. I'm going to compute. Yes, that looks like what I have here. Okay, so I can trust that I put it in correctly. I'm going to stats, I'm going to go to regression, simple linear, x and y. I'm just looking for a linear relationship. I don't need to change anything here. Compute. So as you can see, it gave me a very strong, statistically significant relationship, a negative relationship. My correlation coefficient is negative 0.89. So from the data overall, if I look at it, you see it has that line there. Okay, problem. Not really true, not factual, perhaps not really representative of the data because of this one person or thing or whatever we're measuring. So what's our correlation coefficient? Simplify your answer. So we're going to do negative 0.893. Oh man, let's see to do this all by hand. Oh, I put this in incorrectly anyway. Okay, 8.893. 0.893. You do not have to do this all by hand. Okay, just make sure of that because that seems very intimidating. Is there a linear correlation between x and y? Use alpha equals 0.2. Yes. There is a linear correlation. So the correlation coefficient is in the critical region. Well, we know it's in the critical region because we have the statistical significance of the slope here. We don't have a critical rho value, unfortunately, but that's okay. Also, this is the same. This p-value will probably match this p-value, FYI. You don't need to really worry about that, but yes, I'm going to say that. Okay. All right. So A and B, we've done this now with this outlier here. We're going to continue on. What is the correlation coefficient when the point 10.2 is excluded? Okay, I'm going to get rid of that now. I'm going to say this wrong. I'm going to clear it. I didn't do that. I'm going to clear it. I'm going to look at it, make sure that I have the right data. This is just me kind of really going through all my steps. Yep, big box. I'm going to go stat, regression, simple linear. Repeat my steps now just without that data. Compute. 0. And 0 correlation coefficient means that there is no relationship. P-value of 1. Straight line through my data. What is the correlation coefficient? 0. Okay. Continue. Is there a linear correlation between x and y using alpha equals 0.01? No. Because it is in the oh, nope, sorry, got that wrong. Final check, great. Yes, because it is not in the critical region. Critical region being outside of what we say would be statistically significant. It's hard to kind of visualize that here, but there's not like a normal distribution kind of thing that we can look at as easily. Anyway, it doesn't really matter. Okay, so that's right. So if we continue on, what do you conclude about the possible effect from a single pair of values? A single pair of values does not change the conclusion. the effect from a single pair of values can change the conclusion. And that's what we saw here. So what we saw rather convincingly, I would say, is that we went from a value that was very highly statistically significant with a very large negative relationship, and we removed one data point, this one here, and all of a sudden it drops all the way to 0, meaning there is absolutely no relationship that can be seen. Okay, very clear, very important to know that. Alright, going forward, this is essentially now, I think this is a pretty good question. So we're going to look at this. I'm just going to exit out here because look at all these results I have here. I'm going to reopen this, open in StatCrunch. Here's all my data, so I'm looking at brain volume, the overall size of a person's brain versus their IQ score. I am going to first check what is my claim. Is there official evidence to conclude there's a linear relationship between brain volume and IQ scores? Doesn't seem like it's asking if bigger brains have a larger IQ score, so I'm going to go with B, two-tailed test, check answer, good job. Alright, let's visualize our data. Go to graph, scatter plot, brain volume, IQ score, compute. Looks like this one. Alright, kind of close, pretty close, good job. The linear correlation coefficient, stat, regression, simple linear, brain volume, IQ score. It's important that we know what's predicting what, right? Yes, whatever's on the y-axis is what you're trying to predict. And we're trying to predict IQ score. This is correct. Don't worry about all that. It hasn't asked you anything about that yet. Let's see if we make this a little bigger. There we go. Sample size 20. Correlation coefficient negative 0.03. Very small. Not significant. What is the linear correlation coefficient? Round to 3 decimal places. Negative 0.037. Check answer. Fantastic. The test statistic is... Here with the test statistic is trying to trick us a little bit. So the test statistic was the linear correlation coefficient. But here we're talking about, I believe we're talking about this one. Or we're talking about this one. So this is interesting because essentially when you get into simple linear regression, it's just a different way of doing a t-test and a t-test or an f-test or analysis of variance. It just changes because we're now looking at, instead of groups of data, we're looking between two continuous variables. It doesn't matter. Oh, the statistic T. That makes it a lot more clear. Sorry, I did not see that. I've got to read your things very carefully. Obviously, I did not there. Negative 0.157. Check answer. Fantastic. P-value 0.877. Check answer. Great job. Because the p-value is greater than the significance level point, there is not sufficient evidence to support the claim that there is a linear correlation between brain volumes of twins and the corresponding IQ score for a significance level alpha 0.05. Wonderful. Okay, same one here. This looks about the same. Try it on your own. Good luck. Hopefully this was helpful. If you have any questions, you feel free to reach out. Thanks for watching.